Welcome. In this video we'll be looking at Gaussian elimination, also called row reduction, and studying the echelon forms and reduced echelon form of a matrix arising from a system of linear equations. Just to get us on the same page, remember that our matrices all have entries drawn from the same field. The BI might be our final column if necessary, and we're going to be looking at as just one concept to keep in mind, we say that the dimension of a matrix with n rows and m columns is n times m, or n by m. And we'll come back a little later today, and I guess actually in the next video, we'll come back and talk about several interpretations of the dimension of a matrix. So some basic definitions that we're going to be looking at today. First, we're going to be considering non-zero rows of matrices. So you'll see all but my one center row here is my second row, is my only zero row in this matrix. The other four rows are all non-zero rows. The leading entry of a row is just the first non-zero term. So in my first row, my first non-zero term is 6, then 1, then 2, then 8. For our zero row, you'll note that there's no leading entry in a row of all zeros. Before, in several videos we've looked at, given a system of linear equations, we've converted that into either a coefficient matrix that doesn't keep track of our system of coordinates, or an augmented coefficient matrix where our last column, so this was the BIs that we were considering, keeps track of what all of our linear equations are equal to. So we've also considered, and you guys have already had ample chance to practice, the three basic elementary row operations, where we can either replace one row by a sum of itself and another non-zero row. So we call this adding a multiple of one row to another. We were allowed to swap two rows, so swapping. And we could scale a row up or down by some non-zero constant. So this was for all entries. We multiplied them. One of the reasons that we're learning about these row operations and what we're using them is, our goal is to convert our matrix into something called row echelon form, which this is actually not unique, and we'll talk about this in a second, or reduced row echelon form, which is unique and allows us to immediately read off the solutions to our system of linear equations. We say that, so what these forms mean, we say that we have a system in row echelon form, sometimes just called echelon form, if it has the following three properties. First, we want to have all of our non-zero rows at the bottom. Second, the leading entry of a row is in a column to the right of the leading entry of the row above it. So for each column, the first entry in that row that's non-zero, any row to the left of any column to the left of it should have its leading entries further to the left. So we'll see a couple of examples of this in a second. And finally, all entries in a column below a leading entry are 0. Further, for us to extend it to this reduced echelon form, reduced echelon form is unique. And our conditions for it to be in this reduced echelon form is in addition to our first three conditions. So in addition to these guys, we need the leading entry in each non-zero row to be 1. So we'll scale by whatever constant we need to have our first entry in a row 1. And each leading entry, like each leading 1, is the only non-zero entry in its column. So note that in echelon form, all that we required was that our entries be below that leading entry be 0. In reduced row echelon form, we require that only that entry is non-zero. So we have to find a way to cancel out entries both above and below our leading 1. And one of the advantages of this reduced row echelon form, as I mentioned before, is that we can immediately read off our solution sets. So to give you an idea of what an echelon form would look like for a matrix, here are two matrices taken from our text that have been put into row echelon form. So these asterisks mean they could be any value. So an asterisk is any number in our field. These boxes are what must be a non-zero constant. So non-zero. And you'll note that this both satisfies my leading entries in a row below another row. The leading entry of the second row has to occur after the leading entry of the first row. So another way of putting this is our leading entries are in strictly increasing columns. And all of the entries below a leading entry or a leading term have to be 0, but in row echelon form we don't actually require that these entries up here be forced to be 0. In reduced echelon form, however, we require our leading entries to all be 1s. So whatever matrix was here originally, each of these two rows were scaled to have the first term be 1, and then whatever term remained here was canceled out with addition of a multiple of this row to row 1. So one of the nice properties of these row-reduced echelon forms is that they're unique. So there's one and only one reduced echelon form for a given matrix. So we're going to look at this matrix. So this is the matrix that popped up on one of those first slides today. We'd like to find a way to convert this from this general form into a reduced echelon form, or just echelon form. So we'll start with echelon form first, and then do a reduced echelon form afterwards. So our first step, this is typically the easiest, is we're going to swap this 1, 0 row to the very bottom. So we're just going to swap our second row and our fifth row to obtain this matrix. So you know that these two are identical outside of these two rows have been exchanged. So our matrix A is row equivalent to this. Our goal after removing that is we'd like to remove all leading entries in our first column except for the leading entry in the first row. So we're going to be leaving entry 6 alone, but we'll be looking to get rid of the 1 and the 2 using row operations to cancel them out. So to do that, we'll add to this row, we're going to add, since we need to get a 1 here, we'll take row 3 and replace it with row 3 minus 1/6 of row 1. And to cancel out this 2, we're going to take row 4 and replace it with row 4 minus 1/3 of row 1. So this will give us the matrix you see here. Well, you'll note that I'm actually rounding to the thousandth place here. I'm going to convert these back at the end into whole numbers. So I'm actually, for those of you that have taken numerical analysis or are taking it now, I'm glossing over a little bit of some of the rounding errors that might show up when you guys are checking this in MATLAB. So MATLAB can have rounding problems, so be careful if you're reducing matrices using the software without really thinking. So now that we've gotten our leading entry in row 1, in a column all by itself and had every entry below it in the column set to 0, we're going to move to our next column. Okay, let's change this color. So our next column, our goal is to get 8, which is our leading entry in column 2, to get him in a column by himself. Technically, for echelon form of a matrix, we actually don't have to get rid of this 3. So we don't need to cancel this out. But we do need, for these 3, I guess one of them is already 0, we need to add multiples of row 2 to rows 3 and 4 to get these coefficients of 0, set to 0. So to rows 3 and 4. So for this one, you'll notice that the rounding is a little fuzzier here. I actually did go ahead and cancel out our -3. So I added, since there's 8 here, I guess I added -3/8 copies of row 2 to row 1 to cancel out this. And you can feel free to check this arithmetic on your own. But we continue this procedure iteratively, looking always for the next. Since we're trying to get our leading entry in this column, in this row, in a column to the right, we're going to try to get him alone by himself. So we'll, technically we'd only have to add copies of row 3 to row 4 here to continue to row reduce our matrix into echelon form. I'm going to be a little lazy and knock off the 2 of these as well. This is not required, but it'll make it easier when we convert this into our reduced row echelon form in just a moment. Something you might notice here is that now this row actually has 2 non-zero entries sitting above all zeros. So our next leading term that appears in row 4 is all the way out here in column 5. So we're actually not going to be canceling out this 18 and 16 with any more row operations at the moment. So our next leading entry that we'll be interested in getting by himself is here, is right in this entry. And you'll notice, actually, this is already in row echelon, in just echelon form by our definition. Every leading entry, let me clear some of these out. If you look at our leading entries, are 6, 8, 0.229, and this -0.091. Those 4 leading entries all have every entry below them in their column set equal to 0, and all leading entries of rows before a given row we're examining occur to the left. So to keep getting this into a form that we can then convert into reduced echelon form, we're actually going to do what we did actually on the other 2 slides and convert, cancel out this, using this -0.091, we're going to add appropriate copies of row 4 to rows 1, 2, and 3 to get these entries equal to 0. And so at this point, we've gone as far as we can go in converting our matrix into an echelon form. So again, we actually had in this matrix, technically this is an echelon form. And this is going to differ from our reduced echelon form only by our scaling factors of each of these leading entries in our rows. So our final step to convert this from echelon form into reduced echelon form is we're going to look at those pivot positions, which are exactly the places, let me make this appear, sorry. Our pivot positions are the location of what will be a leading one after I convert this into reduced echelon form. So our pivot positions in this matrix are 1, 1, 2, 2, 3, 3, and 4, 5. So these will be the positions of our leading ones when we convert this into reduced row echelon form. And one of the nice features of this row reduction algorithm is our leading entries in any echelon form will always be in the same position. So no matter how I reduce this matrix, my pivot positions are always going to be 1, 1, 2, 2, 3, 3, and 4, 5. So there are no other ways I could have reduced this to get a different set of pivot positions. So to convert this again into our reduced echelon form, we've already, in each of our rows containing a leading entry besides the first, we've actually already set all of the entries above our leading terms in our pivot positions to 0. So we're most of the way done. All we need to do now is to scale our leading terms and the entire row that they sit in, by whatever I need to rescale that row so the first entry is 1. So we would divide our first row by 6 to get 1, 3, so on. We divide our second row by 8, our third row by 0.229. You might notice a bit of a pattern there. Our fourth row by negative 0.091, and this is our reduced echelon form of a matrix. So while there were actually several different ways that we could, so this reduced echelon form is unique. So it's enough for us to have our leading entries all equal to 1. You'll note that they're in the same pivot positions as the other echelon forms of our matrix. And that's about it. So in the next video, we're going to look at the connection between these row-reduced echelon forms and how we can immediately read off from those what our solution sets look like, and we can parameterize them. And we'll talk about this in the next video. See you guys soon.